Parametric optimization of wire cut EDM process on AISID3 steel using genetic algorithm and gray relation analysis. Abstract: the manufacturing industries are continuously seeking for new and better machining operations in order to achieve the desired profile or contour of their machining parts. In view of this requirement, at present we focused on wire electrical discharge machining process. The wire electric discharge machining, WEDM, is a non-traditional process of material from conductive material to produce parts with intricate shape and profiles. Machine trade has created exponential growth in its producing capabilities in last decade, however still machine tools don't seem to be used at their full potential. Within the gift work, a trial has been created to optimize the machining conditions for surface roughness supported, L9 orthogonal array, Taguchi methodology. Experiments were carried out under varying pulse on time, pulse off time, servo control, and wire feed. An orthogonal array, the genetic algorithm, GA, and gray relational analysis, GRA, were employed to study the surface roughness in the WEDM of AISID3 steel. It was determined that the discharge current was the foremost prestigious factors on the surface roughness. To validate the study, confirmation experiment has been dispensed at optimum set of parameters and expected results are found to be in sensible agreement with experimental findings. Keywords: WEDM, surface roughness, discharge current, genetic algorithm, gray relation analysis. Introduction. Need for unconventional machining processes was extremely hard and brittle materials or difficult to machine material are difficult to machine by traditional machining processes. Once the workpiece is simply too versatile or slender to support the cutting or grinding forces, once the form of the half is simply too complicated. Many sorts of non-traditional machining processes are developed to fulfill additional needed machining conditions. Once these processes square measure used properly, they provide several blessings over non-traditional machining processes. The wire EDM is one of the vital non-conventional machining techniques. The effect of process parameters on the quality of machining, especially surface roughness, is much more crucial. Brajesh Kumarlo, the ET.AL1 studied on optimization of the machining conditions for surface roughness based on L9 orthogonal array, Taguchi methodology. Experiments were distributed below: variable pulse on time, pulse off time, peak current, and wire feed. Joshi ET.AL2 investigated on optimizing the machining parameter of wire electrical discharge machining, WEDM, for multiple performance characteristics on D3 tool steel using principal component analysis, PCA. Shivat ET.AL3 performed wire discharge machining of D3 alloy steel and influence of pulse on time, pulse off time, peak current, and wire speed square measure investigated for MRR, dimensional deviation, gap current and machining time, throughout convoluted machining of D3 alloy steel. Pankaj ET.AL4R studied the effect of various process parameters such as pulse on time, pulse off time and current for high carbon high chromium cold work tool steel, D2. The experiment has been completed with the help of design of experiment by Taguchi method is applied to create an orthogonal array of input variables using the ANOVA. M. Shivakumar ET.AL5 optimum machining parameter for the wire electrical discharge machining of AISID3 steel of two different thickness, 50 mm and 75 mm. Omkar Kulkarni ET.AL6 the experimentation has been completed with the help of Taguchi's L25 orthogonal array. Gray Wolf Optimizer, GWO, algorithm is stimulated by gray wolves. Mangesh ET.AL7 performed CNC wire electrical discharge machining, WEDM, of AL 2124 SICP metal matrix composite, MMC, is analyzed by using dimensional analysis approach, DA, and artificial neural network, N. The various investigations 8 to 12 are carried out on the optimizations of process parameters by using gray analysis and genetic algorithms. Pratik A. Patil ET.AL13 investigated effect of parameter on machining of AISID2 cold work steel through wire cut EDM. This research deals with response surface methodology approach for maximizing the material removal rate in wire electrical discharge machining. Mdarayaraj-et.al14 investigated effect of parameter on machining of SS304 through wire cut EDM. Amitesh Goswami et.al15 analysis trim cut machining and surface integrity of Nimonic ATA alloy using wire cut EDM with 3 levels of input parameters. Somveer Singh Nain et.al16 modeling and optimization of process variables of wire cut electric discharge machining of superalloy Udimate L605. In this paper, an attempt is made to investigate the influence of WEDM process parameters on the performance measures of surface finish and cutting speed while machining of AISID3 steel with 3 levels of process parameters: pulse on time, pulse off time, wire feed and servo control. 2. Selection of material. AISID3 steel, also known as 1.2080, Werkstoff, it is an air hardening, high carbon, high chromium tool steel. It displays glorious abrasion/wear resistance and has sensible dimensional stability and high compressive strength. It's heat treatable and can provide a hardness within the very 58 to 64 HRC. Because of its abrasion resistance within the hardened condition, D3 machining ought to be restricted to finished grinding. The physical and chemical properties of a material are given in tables 1 and 2. 3. Methodology. The following procedure is adopted to pursue the optimization of the process parameters. Selection of material, AISID3 steel. Identifying and selection of various process parameters influencing the machining process. Finalizing the levels and preparing a design of experiments plan by using Minitab software. Conduct the experiment based on design of experiments, calculate the surface roughness and cutting speed. Optimal machining parameters were determined by the Gray relational grade obtained from the Gray relational analysis and genetic algorithm for multi-performance characteristics for surface roughness and material removal rate. A confirmation experiments was conducted by setting the process parameters at optimum level. The order of importance of the controllable factors to the surface roughness and material removal rate are estimated. A Gray relational analysis. Gray relational analysis is an impacting measuring technique in Gray system theory that analyzes unsure relations between one main issue and every one the opposite factors in a very given system. In the case when experiments are ambiguous or when the experimental method cannot be carried out exactly, Gray analysis helps to compensate for the shortcomings in statistical regression. Gray relational analysis is actually a quantity of the absolute value of the data variance between sequences, and it could be used to degree the approximate correlation between sequences. B. Genetic algorithm. Genetic algorithmic rules area unit a kind of optimization algorithm, which means they're accustomed to realize the most or minimum of a perform. Typically speaking, genetic algorithms area unit simulations of evolution, of what kind ever. In most cases, however, genetic algorithms area unit nothing else than probabilistic optimization strategies that area unit supported the principles of evolution. 1. Definition. Assume S to be a set of strings, in non-trivial cases with some underlying grammar. Let X be the search space of an optimization problem as above, then a function C, X, S, X, C, X is called coding function. Conversely, a function C, S, X, S, C, S is called decoding function. In practice, coding and decoding functions, which have to be specified depending on the needs of the actual problem, are not necessarily objective. However, it is in most of the cases useful to work with injective decoding functions. We will see examples soon. Moreover, the following equality is often supposed to be satisfied. COC equals IDS. Finally, we can write down the general formulation of the encoded maximization problem. Find an S0 as such that f equals FOC is as large as possible. 2. Algorithm. T equals 0. Compute initial population B0. While stopping condition not fulfilled do. Begin. Select individuals for reproduction. Create offsprings by crossing individuals. Eventually mutate some individuals. Compute new generation. For experimental work. Experiment has been done on Electronica Sprint Cut Wire Electric Discharge Machine, WEDM, as shown in the figure 4.1. In this work the workpiece material has been taken as a flat having dimensions 150 x 50 x 7 mm thickness. Experiments were conducted on AISID3 steel material and mounted on a WEDM machine tool as shown in figure in 1. The cutting areas of the specimens are 10 x 15 x 7 mm thickness. In the current work, 4 process parameters such as pulse on time, ton, pulse off time, TOF, wire feed rate, WF, and servo control, C/S, were selected for conducting the experiments. The range of experiments was determined from the previous experiments by the Minitab software. Based on Taguchi orthogonal array. Each process parameter was investigated at 3 levels to study the nonlinearity effect of parameters. The selected process parameters and their levels are given in Table 3. And machined specimens are shown in Figure 2. Experiments were conducted by using the WEDM machine on the AISID3 steel and evaluated the surface roughness and cutting speed. The experimental values containing surface roughness and cutting speed are listed in Table 4. V. Results and discussions. A gray relational analysis. In the present study, the workpiece surface roughness and cutting speed in different WEDM parameters are listed in Table 4. In the WEDM process, lower surface roughness and higher cutting speed are indications of better performance. For data pre-processing in the gray relational analysis process, both surface roughness is taken as the lower is better, LB, and cutting speed as higher is better, HB. Let the results of 9 experiments be the comparability sequences XO, K, I equals 1 to 9, K equals 1. All the sequences after data pre-processing are listed in Table 5 and denoted as XO, K, and XI, K, for reference sequence and comparability sequence, respectively. The deviation sequences 0.01 can be calculated as follows. The same calculation method was performed for I equals 1 to 9 and the results of all 0.0 for I equals 1 to 9 are given in Table 6. Using Table 6, .max and .min can be found as follows. .max equals 1.00, .min equals 0.00. If all the process parameters are of equal weighting, then is 0.5. The gray relational coefficients and grade values for each experiment of the L9 orthogonal array. According to the performed experiment design, it is clearly observed from Table 7 that the WEDM parameters setting of experiment number 1 has the highest gray relational grade. Therefore, experiment number 7 is the optimal machining parameters setting for minimum surface roughness and maximum cutting speed simultaneously, i.e. the best multi-performance characteristics, among the 9 experiments. In addition to the determination of optimum WEDM parameters for surface roughness and material removal rate, the response table for the Taguchi method was used to calculate the average gray relational grade for each level of the WEDM parameters. The gray relational grade values for each level of the WEDM parameters were calculated using the same method. The gray relational grade values are shown in Table 8. Since the gray relational grade represents the level of correlation between the reference sequence and the comparability sequence, the greater value of the gray relational grade means that the comparability sequence has a stronger correlation to the reference sequence. In other words, regardless of category of the performance characteristics, a greater gray relational grade value corresponds to better performance. Therefore, the optimal level of the machining parameters is the level with the greatest gray relational grade value. An asterisk indicates that the level value results in a better machining performance. Based on the gray relational grade values given in Table 7, the optimal machining performance for both the surface roughness and the material removal rate was obtained as pulse on time 116s, level 3, pulse off time 45s, level 1, wire feed rate 3 mm per minute, level 3, and servo control 80%, level 3, as best combination. The optimal WEDM parameters levels can be shortly given as A3, B1, C3, and D3. The optimum value obtained are 0.312 for pulse on time, 0.283 for pulse off time, 0.300 for wire feed rate and 0.297 for servo control. The most effective factor affecting performance characteristics is determined by comparing these values. These comparisons will give the level of significance of the controllable factors over the multi-performance characteristics. The most effective controllable factor was the maximum of these values. B. Genetic algorithm. In genetic algorithm, by using Minitab 17 software, the regression equation is generated with the helping of input parameters. Regression equation obtained for surface roughness. For multi-response optimization, the regression equations of surface roughness and cutting speed are combined. To get multi-response regression equation, the individual regression equation is multiplied with weight values W1 and W2, where W1 equals W2 equals 0.5. W1 RA equals -7.14 plus 0.0736x, 1, -0.0035x, 2, plus 0.00665x, 3, -0.118 x, 4. W2 VC equals -5.265 plus 0.0575x, 1, plus 0.00225x, 2, -0.00185x, 3, plus 0.0185 x, 4. Regression equation for multi-response. W1 RA W2 VC equals -1.875 plus 0.0161x, 1, -0.00575x, 2, plus 0.0085x, 3, -0.1365x, 4. These regression equations are copied in the MATLAB software. In MATLAB, the script files are written to the regression equations. Genetic algorithm technique is selected by using OptimTool code in MATLAB software. The multi-objective optimization is done for both surface roughness and cutting speed by combining corresponding regression equations. The optimal process parameters are given in Table 9. The confirmation test was conducted to verify the accuracy of the analysis. The confirmation experiment was conducted at optimum combinations. The response values obtained are as follows: surface roughness equals 1.4572, cutting speed equals 3.42. From the Table 10, by using GRA, the optimal values obtained are: surface roughness is 2.5875 and cutting speed is 3.03 at machining conditions of pulse on time 116s, pulse off time 45s, wire feed rate 3m/min and servo control 80%. By using GA, the optimal values obtained are: surface roughness is 1.33 and cutting speed is 3.42 at machining conditions of pulse on time 108s, pulse off time 55s, wire feed rate 3m/min and servo control 60%. 6 conclusions. Wire electric discharge machining were conducted on AISID3 material with varying 4 parameters such as pulse on time, pulse off time, wire feed rate and servo control. The important conclusions are the following ones. A. Factors like pulse on time, pulse off time, wire feed rate and spark gap voltage have been found to play a significant role in rough cutting operations for minimization of surface roughness and maximization of cutting speed. B. By using GRA, the optimal values obtained are: surface roughness is 2.5875 and cutting speed is 3.03. C. By using GA, the optimal values obtained are: surface roughness is 1.4572 and cutting speed is 3.42. D. The surface roughness value decreased by 43.68% and cutting speed value increased by 12.87%. It shows that GA gives the best optimal values as compared to GRA.